Minimax learning of interpretable factored stochastic policies from conjoint data with uncertainty quantification. Authors: Connor T. Jerzak, UT at Austin. Priyanshi Chandra, Faculty of Informatics, Università della Svizzera Italiana. Rishi Hazra, Departments of Statistics and Economics, Harvard College. Abstract: we study offline policy optimization over exponentially large factorial action spaces from randomized preference data. We show how conjoint experiments can estimate interpretable stochastic policies with asymptotically valid uncertainty under regularity conditions. Conjoint analyses typically report average marginal component effects, or AMCEs, by averaging over opponent attributes. This approach ignores strategic interdependence. We instead learn stochastic interventions, product-of-Categorical's policies over factor levels. These policies optimize expected outcomes in an average case setting and extend to a two-player minimax, or adversarial, setting that realistically captures simultaneous strategic candidate selection. Methodologically, we derive a closed-form optimizer for a tractable two-way interaction regime with L2, variance regularization. We also provide a general gradient-based procedure for richer model classes. Uncertainty from the outcome model propagates asymptotically to both the optimal policy and its value through a delta method approximation. We further model institutional details such as primaries inside the minimax objective and introduce a data-driven measure of strategic divergence between parties. On synthetic data, we empirically characterize finite sample error and coverage as dimensionality and sample size, and vary on a United States presidential conjoint. Adversarially learned policies produce restricted equilibrium vote shares that align with historical election ranges in our data, in stark contrast to non-adversarial averaging optimizers. Introduction. Over the past decade, conjoint analysis, an application of high-dimensional factorial design, has become the most popular survey experiment methodology for studying multidimensional preferences. It is widely used across disciplines to evaluate complex, multi-attribute subjects, including consumer products, job applicants, public policies, and political candidate profiles. In these experiments, respondents may be asked to choose between two hypothetical political candidates whose features are randomly selected. These features might include gender, race, age, education, partisanship, and policy positions. The design often uses a forced choice format, where respondents must select one of the two candidates without an option to abstain or express no preference. Researchers then estimate the average causal effect of each feature while marginalizing the remaining features over a chosen distribution. This popular quantity of interest is called the Average Marginal Component Effect, or AMCE. AMCE. S average A features effect over a chosen distribution for the other features. This means that the answer depends on the averaging choice. In practice, researchers often use a uniform distribution, but real candidate pools are not uniform, and candidates do not choose their profiles in strategic isolation from opponents. We therefore replace effect estimation with policy learning. Instead of asking for the marginal effect of a single attribute, we learn a factored stochastic policy over full profiles. This is a mixed distribution that assigns independent categorical probabilities to each attribute level, while remaining interpretable. For example, one can read off how much weight the policy puts on the economy versus immigration as a policy priority. In the non-adversarial average case setting, this policy is chosen to maximize expected win probability against a fixed reference distribution for the opponent. We control variance and preserve interpretability by shrinking the learned policy toward the experimental assignment. To capture strategic interaction, we extend to an adversarial setting in which both sides simultaneously choose their own mixed profile distributions. The objective is minimax. Each side selects a profile distribution that is best against the other side's distribution, and institutional details are built in. Specifically, we model two stages, primary elections within each party, which induce a distribution over nominees, followed by the general election. The resulting restricted equilibrium policies reflect how strategic opponents and institutions jointly shape feasible profile choices. Under a linear outcome model with two-way interactions, The average case optimizer with squared distance regularization has a closed-form solution. Uncertainty for both the optimal policy and its value is obtained by propagating the outcome model uncertainty forward, using implicit differentiation. The same recipe admits richer models, such as generalized linear models, or GLMS, and Bayesian neural networks. The same machinery also applies when we move from average case learning to adversarial, institution-aware games. The machine learning problem here is therefore offline policy optimization over a combinatorial discrete action space, whose size grows exponentially with the number of attributes. It is not only the estimation of conjoint effects. The product-of-Categorical's restriction gives a tractable and attribute-readable policy class. The closed-form result characterizes a two-way regime, where this optimization can be solved analytically, while the differentiable and Minimax extensions cover richer GLM and neural objectives. The uncertainty layer connects the learned stochastic policy to trustworthy machine learning by propagating outcome model uncertainty into both policy probabilities and values. In sum, our contributions are as follows. First, we shift from AMCEs to a conjoint estimand that is a factored stochastic policy over profiles. This policy is learned to maximize expected performance and remains interpretable at the attribute level. Second, we provide a closed-form average case optimizer under two-way interactions with squared distance variance control, together with uncertainty quantification for both the optimal policy and its value through the delta method. Third, we provide a general gradient-based procedure for richer outcome models, including regularized GLMS and neural models, with end-to-end differentiation for standard errors. Fourth, we introduce an adversarial Minimax extension that embeds institutional structure, with primaries followed by the general election. This yields restricted equilibrium mixed strategies and a data-driven measure of strategic divergence between parties. Fifth, we provide empirical evidence from simulations and a United States presidential conjoint showing that adversarially learned policies produce restricted equilibrium vote shares aligned with historical ranges. We also provide an open-source mapping of historical candidate features to conjoint levels to facilitate replication. Background: conjoint as policy learning. Conjoint analysis is a factorial survey experiment in which respondents evaluate multi-attribute profiles. In a typical forced choice design, each respondent sees two hypothetical profiles, such as political candidates with attributes like age, gender, and policy positions, and must select one as preferred. The experimenter randomizes attribute levels independently across profiles, often with uniform probability. In the language of offline learning, this randomization serves as the logging policy. The dominant approach estimates the average marginal component effect, or AMCE, the expected change in selection probability when a single attribute shifts from a baseline level to a treatment level, averaging over all other attributes. Extensions include the average marginal interaction effect, or a MIE, for two-way interactions. These estimands describe marginal effects under a chosen marginalization distribution. They answer the question, what is the effect of changing one component? We take a different perspective. Instead of estimating marginal effects, we learn a policy, a distribution over full profiles that maximizes expected outcomes. This shift matters when attribute interactions are present. Consider a hiring conjoint, where quantitative skills and communication skills each have positive main effects, but their interaction is negative because they act as substitutes. An AMCE-based approach might select both attributes at high levels, whereas the optimal policy may diversify, placing probability mass on profiles that emphasize one skill or the other. Our framework maps naturally to offline contextual bandits with combinatorial actions. A profile is the combinatorial action vector, the full attribute configuration. The conjoint randomization is the logging policy. The choice outcome is the reward, represented by a 0-to-1 selection indicator. A factored policy is the interpretable product-of-Categorical's policy class. The average case setting is offline policy learning against a fixed opponent or environment. The adversarial setting is a zero-sum game where both players optimize simultaneously. Because profile pair assignment is randomized, conjoint data sidestep behavior policy confounding that arises in observational offline reinforcement learning. However, the framework still requires the outcome model, positivity, and policy class assumptions stated below. Counterfactual outcomes can then be evaluated through direct modeling or off-policy estimators. Classical zero-sum results and modern first-order minimax methods usually optimize over full mixed strategies with known utilities. Here, utilities are estimated from randomized conjoint data, uncertainty is carried forward, and the target is a restricted factored minimax policy. Additional related work context appears later in the paper. Example 1. Consider a simple conjoint with D equals 2 factors and L equals 2 levels for each factor. The first factor is experience, with 2 levels, outsider and insider. The second factor is ideology, with 2 levels, moderate and hardline. A profile such as outsider and moderate is one of 2 squared equals 4 possible attribute combinations. A factored stochastic policy assigns independent probabilities to the factor levels. For example, the policy might assign probability 0.7% to outsider for experience and probability 0.6% to moderate for ideology. Under the product structure, the probability of the outsider moderate profile is 0.7 times 0.6, which equals 0.42. Why not just maximize AMCEs? Suppose outsider has a positive main effect of plus 5%, and moderate also has a positive main effect of plus 3%, but their interaction is negative 6%. In this example, outsider moderates are seen as lacking credibility. An AMCE-based policy would select outsider and moderate, ignoring the interaction. Our method accounts for interactions and may instead place probability mass on outsider and hardline, or on insider and moderate, yielding higher expected outcomes. Methods. Learning factored stochastic policies from conjoint data. We first define the forced choice potential outcomes and the randomization assumptions that identify counterfactual choice probabilities. We then move from an average case policy objective to factored stochastic policies, outcome modeling, and the closed-form two-way optimizer. The remaining subsections describe differentiable optimization with uncertainty propagation, the adversarial minimax extension, and strategic divergence diagnostics. Setup and identification. Suppose we have a simple random sample of n respondents from a population. We consider a conjoint design of candidate choice with d factorial features per candidate. Each feature, indexed by d, has at least 2 levels. A complete candidate profile is called profile T. The set of all possible profiles is called the profile space. Usually, each respondent faces a choice between 2 candidate profiles, one for candidate A and one for candidate B. Let M sub I of profile T denote respondent I's systematic utility for that profile. The realized utility for candidate A with profile T is the systematic utility of profile T plus a candidate a specific shock. The realized utility for candidate B with profile T prime is the systematic utility of profile T prime plus a candidate B specific shock. These shocks are continuous and exchangeable across arms, conditional on profiles and respondent characteristics. The pairwise potential choice outcome. C sub I of profile T and profile T prime equals 1. If respondent I would choose candidate A with profile T over candidate B with profile T prime, and equals 0, otherwise. The observed outcome is the potential choice corresponding to the 2 profiles actually shown to the respondent. We use C for forced choice outcomes. We use Y for generic policy learning outcomes outside the forced choice notation. Because the utility shocks are continuous, ties have probability 0. If the 2 candidates have identical profiles, exchangeability implies that the probability of choosing candidate A is 1/2. More generally, define the shock difference as the candidate B shock minus the candidate A shock, and let F delta be its conditional cumulative distribution function. Then the probability that candidate A is chosen, given profiles T and T prime, is F delta evaluated at the difference between the systematic utility of profile T and the systematic utility of profile T prime. In the standard logit special case, F delta is the logistic sigmoid function. For example, This arises when the arm-specific shocks are independent type 1 extreme value draws with a common scale, so that the shock difference is logistic. With unit scale, the probability that candidate A is chosen is the logistic sigmoid of the systematic utility difference. The sigmoid of x is 1 divided by 1 plus e to the negative x. Often, each treatment combination is equally likely. In that case, every profile has probability 1 divided by the size of the profile space. When factor levels have different assignment probabilities, some profiles are more likely than others. Often, each factor is assigned independently using categorical draws. In that case, the probability of profile T is the product over all features of the assignment probability for the level that profile T takes on that feature. We call the vector of these original assignment probabilities the logging distribution, P. For simplicity, we make standard assumptions. We assume no interference between units. We also assume randomized profile pair assignment. The full set of potential choices is independent of the assigned candidate A and candidate B profiles. Finally, every admissible profile pair in the experimental design has positive probability. Average case policy objective. One approach in policy learning is to identify the single treatment combination that maximizes the average value of a generic outcome. In words, the optimal profile, T star, is the profile whose potential outcome has the largest population mean. In the forced choice conjoint case, this becomes the candidate A profile that maximizes candidate A's expected choice probability, averaging over the features of candidate B. This is analogous to AMCE analysis, where the opposing candidates' features are averaged over. This approach has two limitations. First, high-dimensional treatments in conjoint analysis make it difficult to estimate the best profile non-parametrically, because the number of possible profiles can far exceed the sample size. Second, when several profiles are equally optimal, learning a set of strong profiles is more informative than learning only one. To address this challenge, we propose an optimal stochastic intervention. Instead of choosing one profile, we choose a parametric distribution over profiles. We call this distribution a policy, and denote it by pi. The policy value Q of pi is the sum over profiles of the expected outcome, under each profile times the probability that policy pi assigns to that profile. The optimal policy, pi star, is the policy that maximizes this value. In the forced choice conjoint case, the average case policy value for candidate A is defined by averaging over both candidate A and candidate B profiles. For every candidate A profile and every candidate B profile, take the expected choice outcome for candidate A, multiply it by the probability that candidate A's policy assigns to the candidate A profile, and multiply again by the probability that the logging distribution P assigns to the candidate B profile. The sum of these terms is Q of candidate A's policy. The optimal candidate, a policy, is any candidate, a policy that maximizes this average case value. This policy characterizes the highest attainable vote share for candidate A under a counterfactual strategy for assigning candidate A characteristics, while candidate B features are drawn from a fixed averaging distribution, such as the uniform distribution. Restricted factored policies. We preserve interpretability by restricting candidate A's counterfactual profile distribution to the same product-of-Categoricals form used by the conjoint randomization. That is, candidate A's policy assigns probabilities independently across attributes, using policy probabilities Pi in place of the logging probabilities P1. This restriction yields an attribute-readable policy and keeps off-policy evaluation tractable. The deterministic best profile is a degenerate special case, where the policy assigns probability 1 to a single profile, but in high-dimensional conjoints, that target is not reliably estimable and is statistically brittle. We therefore optimize over stochastic policies that summarize families of high-performing profiles. To allow meaningful deviations from the design while controlling variance, we impose an L2 or KL trust region around the logging distribution P. In the L2 version, the objective is the policy value Q of candidate A's policy minus lambda n times the squared Euclidean distance between candidate A's policy and the logging distribution P. Equivalently, We can constrain the distance between the policy and the logging distribution to be no larger than a specified radius. This regularization is motivated by the increase in off-policy variance as the policy moves away from the logging distribution. The combination of restriction and regularization matters because it preserves interpretability, stabilizes estimation, and yields a closed-form average case optimizer under two-way interactions. It also still allows general gradient-based solutions for richer outcome models, including neural outcome models, restricted policies as variational approximations. When the variance control regularizer is KL divergence, the unrestricted optimal policy over the full simplex has a Gibbs or log linear form. In words, the optimal probability of a profile is proportional to the logging probability of that profile times the exponential of its utility divided by the regularization strength. Restricting this full policy to product-of-Categorical's policies is exactly the classical mean field, or product form, variational approximation to the Gibbs distribution. The Gibbs distribution is the theoretical unrestricted perfect strategy. The product policy is its interpretable approximation. Outcome models. Bernoulli GLM. Let C sub I denote the forced choice made by respondent I. We model this choice as a Bernoulli random variable whose success probability is the logistic sigmoid of a linear predictor ETA sub I. For candidate C, define the main effect indicator for feature D and level L as 1 if candidate C's feature D takes level L, and 0 otherwise. Define the two-way indicator for feature D at level L and feature D prime at level L prime as 1 if candidate C has both of those feature levels, and 0 otherwise. The linear predictor, eta sub I, is the sum of two parts. The first part is the sum over all features and levels of the main effect coefficient beta times the difference between candidate A's main effect indicator and candidate B's main effect indicator. The second part is the sum over all pairs of features and levels of the interaction coefficient gamma times the difference between candidate A's two-way indicator and candidate B's two-way indicator. Here, beta denotes a main effect, and gamma denotes a two-way interaction effect. We impose sum to zero constraints on the main effects and on each set of two-way interactions for identifiability. The intercept is constrained to 0 to enforce forced choice antisymmetry. Reversing the two profiles reverses the sign of the linear predictor. This implies that when the two candidates have identical profiles, candidate A is chosen with probability 1/2. The beta and gamma parameters are estimated by generalized linear modeling, with optional lasso sparsity for selection followed by an unpenalized refit when inference is required. The intuition is that the difference between candidate A's utility and candidate B's utility defines the choice between them. When the linear in indicators GLM is too restrictive, a natural alternative is a Bayesian neural network outcome model. Scope of parametric assumptions. The linear probability approximation used below is only for the closed-form two-way optimizer. It is not required by the broader framework. The same policy objective can be optimized directly under Bernoulli GLMS and Bayesian neural outcome models using gradient methods, with uncertainty propagated through the fitted outcome model. Linear in indicator specifications are standard starting points for randomized forced choice conjoint analysis. Later robustness results quantify sensitivity to nonlinear response surfaces. Closed form average case optimizer. For the Bernoulli GLM, the average outcome is the expected value of the logistic choice probability when candidate A and candidate B profiles are drawn from their respective policies. This objective is optimized numerically by the methods described later. The closed form result in this subsection applies to the corresponding linear probability approximation, where the conditional choice probability is linear in the profile indicators. The stochastic intervention under forced choice conjoint can be described as follows. The policy value Q of candidate A's policy and candidate B's policy is the expected choice probability for candidate A when candidate A's profile is drawn from candidate A's policy, and candidate B's profile is drawn from candidate B's policy. The linear predictor is the same main effect and two-way interaction score described above. Main effects compare candidate A's and candidate B's indicators, and interactions compare candidate A's and candidate B's two-way indicators. Under the linear probability approximation, Q equals 1/2 plus the main effect advantage of candidate A over candidate B, plus the interaction contribution from candidate A's policy minus the interaction contribution from candidate B's policy. More explicitly, each main effect coefficient beta is weighted by the difference between candidate A's probability and candidate B's probability of assigning that feature level. Each two-way interaction coefficient gamma is weighted by the product of candidate A's marginal probabilities for the corresponding two feature levels, and then the analogous candidate B interaction product is subtracted. The constant 1/2 is fixed by forced choice symmetry and does not affect the optimizer. We therefore omit it from the stationary first-order system. Motivated by opponent marginalization in AMCE analysis, we first consider the average case optimal stochastic intervention, where candidate A optimizes against a fixed distribution over candidate B's features. Candidate B's features may be assigned according to the logging distribution P, or according to another fixed distribution such as the uniform distribution. We call this the average case optimal stochastic intervention for forced choice conjoints because candidate B is static. Before applying the closed form result, we re-express the linear probability approximation in baseline coordinates. For each factor D, take the final level as the baseline. We include indicators only for the non-baseline levels. The probability of the baseline level is 1 minus the sum of the non-baseline probabilities for that factor. If the outcome model was estimated with sum to zero main effects and interactions, we transform those coefficients into baseline-coded coefficients. The baseline-coded two-way interaction for two non-baseline levels equals the original interaction for those two levels, minus the interaction involving the baseline of the first factor, minus the interaction involving the baseline of the second factor, plus the interaction involving both baselines. The baseline-coded main effect for a non-baseline level equals the original main effect contrast against that factor's baseline, plus interaction adjustments involving the baselines of the other factors. For later indexed factors, add the interaction between the current non-baseline level and the other factor's baseline, minus the interaction between both baselines. For earlier indexed factors, add the corresponding baseline interaction in the reversed order. Proposition 1. Under the baseline-coded linear probability approximation with two-way interactions, the L2 regularized average case objective has a closed-form stationary solution. The solution is obtained by solving the linear first-order conditions for the non-baseline policy probabilities. In this system, the baseline-coded main effects determine the linear payoff terms. The baseline-coded two-way interactions determine the cross-feature curvature. The L2 regularizer contributes negative curvature that shrinks the policy toward the logging distribution P, with within-factor terms reflecting the simplex constraint that non-baseline probabilities and the baseline probability must sum to 1. If the regularization strength lambda n is large enough that the Hessian is negative definite, and if the resulting solution lies in the interior of the simplex for every factor, then this stationary point is the unique global maximizer. If the linear system solution violates non-negativity or lies on the simplex boundary, it should not be interpreted as the constrained optimizer. In that case, one must solve the corresponding constrained quadratic program with simplex constraints, or use the logit parameterized gradient method described below. The optimal stochastic intervention is a deterministic function of the outcome model parameters. These parameters, beta and gamma, are not known in advance, but can be estimated with a GLM. Uncertainties can be calculated using asymptotic standard errors from the unpenalized model. If a post-selection refit is used, these standard errors condition on the selected specification, unless a valid post-selection or sample splitting procedure is used. Intuitively, this analysis lets researchers investigate the implications of candidate choice models fit to the data. Instead of examining marginal effects through AMCEs, researchers can examine joint effects by looking at the optimal behavior implied by their chosen model. Estimates of the optimal distribution over candidates are generated from uncertain model parameters, and the delta method propagates that uncertainty asymptotically. Because the optimal policy and its value are deterministic functions of the estimated outcome model parameters, their variance-covariance matrix can be obtained by the delta method. In words, the variance-covariance matrix for the estimated optimal policy value and the estimated optimal policy equals the Jacobian times the estimated covariance matrix of the outcome model parameters times the transpose of the Jacobian. The Jacobian contains the partial derivatives of the estimated policy value and the estimated optimal policy with respect to the estimated beta and gamma parameters. This result relies on three regularity conditions. First, the first stage estimator is asymptotically normal under independent sampling and correct specification. Second, the regularized objective has a unique interior maximizer, and the map from the outcome model parameters to the optimal policy is differentiable at the truth. Third, optimization error is smaller than the order of n to the negative 1/2. Under these conditions, the square root n scale difference between the estimated policy summary and the true policy summary converges in distribution to a normal distribution with mean zero and covariance given by the delta method sandwich expression. General differentiable optimization and uncertainty. There are limitations to the approach just described. The analytical solution in Proposition 1 does not guarantee that the estimated optimal policy probabilities are non-negative when the regularization parameter is small. Also, once we generalize the outcome model to a generalized linear model or to interactions beyond two-way terms, we no longer have a known analytical formula for the optimal solution. To address these limitations, we can compute the stochastic intervention optimization iteratively instead of relying on an analytical closed form. To ensure that the estimated optimal policy lies on the probability simplex, we reparameterize the objective using unconstrained alpha parameters. For each factor, the alpha values are transformed into probabilities using a softmax type mapping. Each non-baseline level receives probability proportional to the exponential of its alpha value, while the baseline level receives the remaining normalized probability. This guarantees that all probabilities are non-negative and sum to 1 within each factor. For the average case one-player objective, standard compactness, boundedness, and step size conditions imply that projected gradient methods have stationary limit points. Under additional strict saddle and non-degeneracy assumptions, random initialization avoids strict saddles with probability 1. We update the unconstrained parameters using gradient information from the objective. At each iteration, the alpha vector is moved in the direction of the gradient of the objective, with the step size controlling how far the update moves. For delta method inference, gradients are traced through all optimization updates when computing the Jacobian. Approximate inference then proceeds analogously to the closed-form case using a first-order delta method. With a closed-form expression for the estimated optimal policy, the derivative of the optimal policy with respect to the regression parameters can be written directly using the closed-form Jacobian. When the estimated optimal policy is obtained iteratively, we can still consider the same derivative. Although closed-form derivatives of the iterative solution may be unknown, automatic differentiation can evaluate them by tracing the gradient information through the full sequence of gradient ascent updates. For a fixed number of iterations, the ascent procedure defines a deterministic mapping from the fitted outcome model parameters to the estimated optimal policy, and then to the estimated value of that policy. Reverse mode differentiation can backpropagate through the entire unrolled sequence and yield the required Jacobian. Alternatively, we can avoid differentiating through a long optimization trace by applying implicit differentiation to the stationarity conditions at the converged solution. Let the first-order optimality mapping be the gradient of the objective with respect to the alpha parameters, evaluated at the outcome model parameters. In the adversarial case, this mapping stacks the signed gradients for both players. If this mapping is continuously differentiable, and if its Jacobian with respect to the alpha parameters is non-singular at the estimated fixed point, then the implicit function theorem gives the derivative of the optimal alpha parameters with respect to the outcome model parameters. As a result, the delta method Jacobian for the optimal policy and its value can be obtained by solving a linear system involving this Jacobian, rather than backpropagating through every gradient step. This implicit approach is usually cheaper and more memory efficient for long trainings, and it agrees with unrolling when the optimizer has converged to the same fixed point. However, it can be unstable when optimization has not converged, when the Jacobian is ill-conditioned or singular, or when the solution lies near a boundary. Adversarial minimax policies. Thus far, we have considered optimal stochastic interventions under the assumption that one party, or candidate, chooses its profile distribution to maximize expected vote share while treating the opposing candidate's profile distribution as fixed. This framework is useful in settings without direct strategic interaction, such as analyzing hiring choices. It is less suitable when two agents strategically select their own profiles in direct competition. In many contexts, both the focal candidate and the opposing candidate are engaged in simultaneous strategic optimization. To capture these adversarial dynamics, we introduce an adversarial case optimal stochastic intervention framework. This framework explicitly models two agents, labeled Candidate A and Candidate B, each attempting to maximize their expected probability of victory in a forced choice setting. This is a two-player, simultaneous action, zero-sum game. For each respondent, the systematic utility of a candidate depends on that candidate's randomly drawn profile. Under the same exchangeable shock formulation as above, candidate A wins a pairwise forced choice when A's utility for the respondent is greater than B's utility for that respondent. We define candidate profile distributions for A and B separately. Each distribution assigns probabilities to the set of all possible profiles. The use of a stochastic or mixed profile distribution, rather than a deterministic profile, follows from the combinatorics of possible profiles and the practical impossibility of estimating a single optimal profile with finite samples. We consider a zero-sum environment where one candidate's gain is the other candidate's loss. The optimal profile distributions are characterized through a minimax optimization problem. Candidate A chooses a policy to maximize, while candidate B chooses a policy to minimize A's expected win probability. In the unrestricted simplex, neither candidate can improve expected performance by unilaterally changing their distribution. Such a pair of optimal distributions constitutes a Nash equilibrium for the adversarial environment. In other words, given B's equilibrium distribution, no deviation from A's equilibrium distribution improves A's performance, and given A's equilibrium distribution, no deviation from B's equilibrium distribution improves B's performance. In our restricted factored class, we instead target stationary points of the restricted minimax objective. Institutional constraints. Without institutional asymmetries, the adversarial game just described can admit trivial or symmetric equilibria. Real strategic environments, such as elections, are structured by rules that determine how agents interact, including who votes and when. These rules shape both strategies and equilibria. We model a general two-stage system, for example party primaries followed by a general election, under potentially asymmetric institutions across competitors. Let A and B denote the two competing agents, such as political parties. Each has a first-stage participant set. In the electoral example, these are the possibly overlapping primary electorates, with closed, semi-open, and open primaries as special cases. There is also a final stage participant set, corresponding to the general election electorate. Institutions determine these participant sets and their sampling weights, such as turnout rates and the inclusion of independents. We bundle these institutional parameters together. Each agent chooses a factored product-of-Categorical's mixed profile distribution, which we call that agent's policy. The rest of that agent's field is summarized by a counter distribution. Institutionalized value. Given nominees drawn from the induced nominee distributions for A and B, the probability that A wins the general election is the average, over the general electorate, of the probability that a respondent prefers A's nominee to B's nominee. In the standard logit special case, this probability is given by the logistic transformation of the difference between the respondent's systematic utility for A's nominee and the respondent's systematic utility for B's nominee. More generally, it is given by the distribution of the difference in the unobserved shocks. The expected payoff to A is then the average general election win probability, taken over nominee draws induced by A's and B's policies, their counter distributions, and the institutional rules. Equilibria under institutions. The minimax problem over interpretable, variance-controlled policies uses factored product-of-Categorical's distributions for both candidates, with the counter distributions treated as fixed. This defines a restricted minimax problem. Candidate A chooses a factored policy to maximize the institutional expected payoff, while candidate B chooses a factored policy to minimize that same payoff. When the institutional mapping from strategy distributions to nominee distributions is affine in each player's mixed strategy, holding the opponent and counter distributions fixed, the institutional expected payoff is bilinear on the full mixed strategy simplices. In that case, von Neumann's Minimax theorem guarantees a full simplex saddle point. Without this affine and bilinear structure, that existence conclusion does not follow. Within the restricted factored class, the policy class is generally non-convex, so a saddle point need not exist within the restricted class. In practice, we compute a stationary point using gradient ascent for candidate A and gradient descent for candidate B on unconstrained logits. Payoff-based exploitability diagnostics can then quantify the largest unilateral improvement available against the learned pair of policies. Guarantees. The regularized payoff is the institutional expected payoff to A, minus a penalty for how far A's policy is from a reference policy, plus a corresponding penalty for how far B's policy is from that same reference policy. This payoff is concave in A's policy and convex in B's policy whenever the institutional expected payoff is bilinear in the full mixed strategies. In that convex-concave full simplex setting, extragradient and mirror-prox methods converge with explicit primal dual gap rates. A factored logit parameterization is generally non-convex, so the ascent-descent solver used below should be interpreted as computing a restricted stationary point, with its quality assessed using exploitability diagnostics. As in the average case, delta method inference follows by differentiating the resulting objective. This can be done either by backpropagating through the unrolled optimization trace or by implicit differentiation of the stationarity conditions at the fixed point. The result is a set of standard errors for the estimated nominee distributions for A and B, and for the estimated institutional expected payoff. Remarks. First, open versus closed primaries, heterogeneous turnout, and the participation of independents are encoded through the institutional parameters by changing the composition and weighting of the primary electorates and the general electorate. Second, hard rules, such as eligibility constraints or ballot access requirements, can be enforced by restricting the support of each candidate's policy to admissible profiles. Third, multi-round or multi-candidate primaries can be accommodated using the appropriate implied choice probabilities. Algorithm. Adversarial Minimax policy learning. Inputs. Forced choice data, institutional parameters, a reference policy, a regularization strength, a regularizer, a learning rate, and the number of optimization iterations. Step 1. Fit the outcome model. Estimate the forced choice outcome model using a generalized linear model or neural network. Step 2. Set up the restricted, non-convex optimization problem. Initialize unconstrained logits for candidate A and candidate B. Define the regularized payoff as the institutional expected payoff to A, minus the regularization penalty for A's policy relative to the reference policy, plus the regularization penalty for B's policy relative to the reference policy. Step 3. Run iterative ascent and descent. For each optimization iteration, update candidate A's logits by moving them in the direction that increases the regularized payoff. Then update candidate B's logits by moving them in the direction that decreases the regularized payoff. Step 4. Convert logits into policies. After the final iteration, apply the softmax transformation within each factor to obtain candidate A's estimated optimal policy and candidate B's estimated optimal policy. Step 5. Estimate nominee distributions. Use Monte Carlo draws over the primary process to compute the estimated nominee distribution for candidate A and the estimated nominee distribution for candidate B. Step 6. Quantify uncertainty. Compute the Jacobian either by differentiating through the unrolled optimization trace or by using implicit differentiation at the fixed point. Then apply the delta method by multiplying the Jacobian, the estimated covariance matrix of the outcome model parameters, and the transpose of the Jacobian. Step 7. Return the learned policies, the estimated institutional expected payoff, the estimated regularized payoff, and standard errors. Strategic divergence. Unlike a MCE analysis, which cannot quantify observed candidate information through experimental findings. The methodology here enables the measurement of strategic divergence using actual candidate profiles and elicited conjoint preferences. Given the optimal candidate distribution for one party and the optimal candidate distribution for another party in a given institutional context, we can compute a strategic divergence score for any candidate profile using the estimated strategies. The strategic divergence score compares how likely the same profile is under candidate A's strategy versus candidate B's strategy. It takes the absolute value of the log of the ratio between the probability of the profile under A's strategy and the probability of the profile under B's strategy. A small positive constant is added to both probabilities before taking the ratio, so that the log ratio is always defined, even when one strategy assigns 0 probability to the profile. When the strategic divergence score is 0, the candidate profile is equally likely under the strategic actions of party A and party B. When the score is large, the profile is likely under the strategy of one party, but unlikely under the strategy of the other. Experiments. Average case simulation. In Monte Carlo simulations using synthetic binary conjoint data under a linear outcome model with interactions, scaled so that main effects have r squared equal to 0.70, we assess finite sample convergence of the average case optimal stochastic intervention. We vary sample sizes of 500, 1,500, 3,500, and 10,000, and dimensions of 5, 10, and 20. We use L2 regularization tuned so that the policy diverges moderately from the uniform data generating distribution. Results show negligible bias and rapidly declining root mean squared error, or RMSE, driven mainly by variance, for both the estimated optimal policy and its estimated value, even at small sample sizes. Inference is reliable, with coverage approaching nominal levels across settings. Additional residual simulation figures report bias, root, mean squared error, standard errors, and coverage. This approach also substantially outperforms a baseline AMCE policy that selects the best level factor by factor, achieving higher expected outcomes on average. To assess sensitivity to outcome model misspecification, we also evaluate settings where the true choice surface contains nonlinear structure, while the fitted model is either a GLM with pairwise interactions or a Bayesian transformer. The misspecification summary table shows that the GLM is most efficient and best calibrated when the linear approximation is correct or close, while the transformer can improve root mean squared error under stronger nonlinear misspecification, but has imperfect coverage. Adversarial case simulation design. To assess finite sample performance in the adversarial setting, we simulate two-party strategic competition between Republicans, denoted R, and Democrats, denoted D, in a two-stage electoral process, primaries for nominee selection followed by a general election. Voters are affiliated with either R or D. The Republican voter share takes values 0.2%, 0.3%, 0.5%, 0.65%, and 0.8%, and the Democratic voter share is 1 minus the Republican voter share. Only affiliated voters participate in their party's primary. We vary sample sizes of 1,000, 5,000, and 10,000, with Monte Carlo replications in each cell. In primaries, each party offers two profiles. One profile is selected through the party's mechanism, and the comparison profile is drawn uniformly. Voter choices follow logistic models based on candidate features, using gender to keep ground truth equilibria tractable. General elections then pit the Republican and Democratic primary winners against each other, with all voters choosing according to separate Republican-specific and Democratic-specific logistic models. Ground truth. Mixed strategies for Republicans and Democrats are computed as grid-approximated equilibria over a finite strategy grid, maximizing the expected win probability under the pair of party strategies. For each run, we estimate equilibria and outcomes, evaluating how the Republican voter share and sample size affect performance. We report root, mean squared error, and 95% coverage for the Republican strategy. Adversarial case simulation results. Simulation results indicate that estimation error depends primarily on the conjoint sample size, with only modest sensitivity to the proportion of Republican voters. Larger sample sizes reduce uncertainty by stabilizing estimates of voter utilities. As sample size increases, Overall estimation error declines sharply for all Republican voter shares. Coverage rates fall below the nominal level for a sample size of 1,000, but approach nominal 95% coverage for larger sample sizes. The stronger performance with larger samples reflects more precise utility estimation, which allows better approximations of the restricted Minimax stationary point in two-party adversarial competition. Figure description. The adversarial simulation figure has two panels. The left panel plots root, mean squared error for the estimated Republican strategy across sample sizes and Republican voter shares. The right panel plots coverage probability for 95% confidence intervals for the same strategy. The visual pattern shows lower error and better coverage as sample size increases. Real-world conjoint application, U.S. presidential. We now apply our methods to analyze policy positioning and optimal candidate selection using presidential preference data from Ono and co-authors, 2019. The outcome is a binary indicator for whether candidate A or candidate B was selected by respondent I in a forced conjoint experiment. In the pairwise stochastic choice formulation above, this is the observed forced choice, whether candidate A's profile is chosen over candidate B's profile. Standard errors for delta method. Uncertainty propagation are clustered at the respondent level. The main text reports the neural approach, the appendix reports the GLM approach. Average versus adversarial case results. We optimize expected vote share for subpopulations, including all respondents, Democrats, Republicans, and independents, against a uniform opponent distribution. We fit an outcome model with interactions and propagate uncertainty using the delta method. In the neural average case optimal policy figure, optima diverge on immigration, abortion, and policy expertise, such as economy versus public safety preferences, but converge on personality traits. Under closed primaries, we compute restricted minimax stationary points for Republican versus Democratic strategies. In the neural restricted equilibrium policy figure, the policies differ from the average case policies. For example, Democrats deprioritize immigration in the average case, but counter Republican guest worker stances in the adversarial case. Restricted equilibrium vote shares drop markedly and align more closely with historical elections. Results with data-driven clustering. Prior analyses of regularized optimal stochastic interventions, with and without adversarial dynamics, ignored respondent characteristics beyond party affiliation. Yet heterogeneous voter types often favor distinct candidate profiles. To uncover these differences, we apply optimal stochastic interventions under data-driven respondent clustering, revealing how subgroups respond uniquely to high-dimensional features. Using the clustered outcome model of Goplerud and co-authors, 2022, the covariate sensitive strategy figure shows that the neural approach recovers the underlying Democrat, Independent, and Republican preference structure endogenously, without explicit partisan labels. This highlights the approach's value in non-adversarial settings, where subgroup discovery enables tailored strategies. Historical comparison. In contrast to AMCEs, our methods yield distributions over profiles, enabling likelihood-based evaluation of observed candidates. We map the 2016 primary contenders to the conjoint levels from Ono and co-authors, 2019. When a stance is ambiguous, we average uniformly over plausible levels. The historical comparison figure shows that the average case optimizer, evaluated against a uniform opponent, implies vote shares outside the historical two-party range since 1976. By contrast, the adversarial restricted equilibrium optimizer closely matches the 2016 result and falls within the historical range. We then score each 2016 contender by the log probability of their features under the estimated optimal stochastic interventions. The strategic divergence figure aggregates the strategic divergence factor. Overall, Democratic candidates show somewhat higher divergence. Figure description. The historical comparison figure plots historical U.S. presidential two-party vote shares from 1970 to 6 through 2016, then overlays the model-based average case and adversarial case estimates. The average case estimate lies outside the historical range, while the adversarial restricted equilibrium estimate lies inside that range and close to the 2016 election result. Candidate-level log probabilities are reported in the corresponding table. Limitations. This approach relies on a two-step estimator, and inference requires accessible variance-covariance matrices. The factorized policy class is interpretable and variance stabilizing, but it is an approximation rather than an unrestricted optimum. Uncertainty estimates do not account for preference formation. Inferred strategies also depend on institutional design knowledge, which may be hard to obtain. Impact statement. This work develops tools for transparent preference analysis, uncertainty-aware decision support, and reproducible mapping between observed candidates and conjoint feature spaces. The same tools could be misused for strategic persuasion, manipulative candidate positioning, or micro-targeting. We therefore emphasize uncertainty reporting, public release of mappings and code, and diagnostics, such as the strategic divergence measure, which can also help detect departures between observed candidates and inferred restricted equilibrium policies.